let us go on to the presentation by our friend from Canada, Menciona, and this is John Sherstobitoff, director, and he will be talking about resilience. Please go ahead. Welcome, doctor.
Buenos dias. Good morning, everyone. Are you seeing my screen?
Yes.
Okay, very good. Yes, no, I'm very, very pleased to have been invited by Dr. Alcacer to share what is being done in BC regarding the retrofit of our public schools. So my presentation will briefly go through the history, some of the policy, briefly the technical aspects, a few photos of some upgrades that we've done here, and our path forward. So why did the Ministry of Education prepare standalone, brand new seismic retrofit guidelines for the schools here? It was very haphazard prior to these starting, and they wanted a guideline that would achieve life safety as a minimum for as many of the high-risk schools as possible in a cost-effective manner. And the most important thing is they wanted a common engineering approach that was missing before these guidelines started. So they retained the engineers and geoscientists of BC to manage a team of researchers and engineers from the University of British Columbia, a peer review committee made up of British Columbia structural engineers with seismic experience, an external peer review group from US specialists in earthquake engineering, and then a technical review board that would overview the implementation of this program. The program started in 2004. Various editions of the guidelines were prepared and issued. The current one is called SRG3, the third edition. The next version has been completed, and that's pending release later this year. Every time a set of guidelines was issued, there was a training workshop for the structural engineers, the school district staff, and key ministry staff. And the engineers and geoscientists of BC retains a list of everybody that attended such sessions, and the school districts have been mandated to follow these guidelines for the retrofit of the schools and only use the trained engineers or firms. So again, a brand new document that didn't exist before this started. You can see the various volumes that it includes, test results, library of details, example projects, site-specific response analysis is pending, post-earthquake evaluation, liquefaction guidelines in this manual for the community to use here. So what were some of the key deliverables? There's something called, it's an online tool called an analyzer, and I'll talk to you about that shortly, where it becomes, it's a tool that rapidly allows engineers to do assessment, retrofit design, post-earthquake evaluation for lateral load resisting systems, out-of-plane walls, and diaphragms. And I'll speak to this more in detail. So another key deliverable at the beginning of the program was to assess every school in British Columbia in moderate and high seismic hazard regions. Every piece of the school was broken into structural blocks because schools here in BC have been added on year after year, and each one had a different structural behavior. Initially, all buildings designed 1990 or later were exempt because they had, studies show they met minimum life safety. And a list of all the blocks, these structural blocks in BC, was created with a risk rating, high, medium, or low. Another key deliverable of the program was a custom database. Every school district, every school, every block had all the studies that were developed for them, and this was available to all the engineers to use to look at what was done in other school districts, other buildings, what had been done in the past, and it was a great database for the ministry just to record where the program was. Another key deliverable that was very successful was a technical review board. Every study was reviewed independently by another structural engineer. Every cost estimate was reviewed by another cost estimator. And it proved to be very collaborative. You know, the engineers work, reviewing each other's work. It proved to be very collaborative to make sure the program was implemented as the Ministry of Education expected. So the policy that the ministry put forth to the school districts, every high-risk building had to have this seismic project identification report done. And what the ministry wanted and realized, there was a standard template. The fees for every consultant was uniform, so it was not about, you know, bidding low to get the work. Everybody had the same fees. It was led by structural engineers, and at the end of the day, it was prepared a concept and a cost for a standalone seismic upgrade, including input from the architectural, mechanical, and electrical disciplines to make sure all the removal and reinstatement of those components was included in the cost. And as I said, the technical review board reviewed the structural aspects and the cost aspects. Following that, a project definition report was prepared to send to the ministry to obtain funding for the seismic mitigation of the school or replacement. So at this level, this report looked at what are the options for an individual school. Replace it? Is it more cost effective to replace it? Is it better to just do a standalone seismic upgrade? Or is there some combination and permutation of these? And this now included all the costs for phasing, accommodation, moving costs. Maybe the local authority having jurisdiction required sprinklers or universal accessibility to be added. And all of these, so this was now the true, complete project cost for the ministry to provide funding to the district to implement this project. Okay, so now onto the technical aspect of this. So the seismic hazard that was in these guidelines is consistent with the National Building Code of Canada, Uniform Hazard Response Spectrum, annual exceedance of probability 1 in 2475. 3 sources of earthquakes that we can be subject to here in British Columbia. And again, magnitude 7-ish, and of course a subduction of magnitude 9. So what was done is their analysis was done, and you'll understand this as I go forward. So for each of those 3 earthquake sources, 20 ground motion records were selected, scaled to both high and moderate seismicity levels, scaled to a conditional mean spectra at either 1 second or 0.5 seconds. So at the end of the day, for each of these prototypes that were selected for the studies, 240 ground motion records were analyzed to assess the behavior of each prototype in the system. So in the prototypes, there was lateral deformation resistance systems, shear walls, bracing, and the like. There were 33 unique prototypes consistent with the existing construction and new construction in BC. Unreinforced masonry walls that could collapse out of plane, and flexible diaphragms, wood and steel deck, typical for what we use here. And a wide range of heights and resistances and URM thicknesses were assessed as part of these analyses. So for each prototype, for example, the lateral deformation system prototypes or diaphragms, backbone curves were developed either from experimental or from literature, including the strength degradation of each of those prototypes. And at the end of the day, a design drift limit was specified to achieve life safety, and there was a conditional drift limit to achieve collapse prevention for each of these components. And again, this is just a snapshot of, there's the variety of wood, steel, concrete, masonry, clay brick, prototypes that were assessed in the program, and the kind of maximum drifts that were allowed in the study for life safety performance. Of course, the key in every seismic upgrade is to make sure that the vertical load carrying components remain able to carry the vertical loads. And these are the drift limits for the various types of components to make sure they could carry the vertical load in the event of an earthquake. So here's a cartoon of the fundamental concept of these guidelines. It's all about drift and ensuring, understanding, there's a certain drift in a structure at which there's a very high probability of collapse. This project set a drift, of course, back from that to have a probability of drift exceedance, that this drift that we determined was going to provide this life safety collapse prevention performance, so that this drift had a probability of exceedance of only 2% in the 50-year life of the school after it was upgraded. And the result is to provide to the engineers a % capacity that the existing or new components of the school needed to meet. And again, so for classrooms, we expected a better performance to enable shelter in place after the 1 in 24/75 earthquake. Classrooms, a minimum of life safety. So again, all the buildings that were assessed, and again, this probability of drift exceedance in 50 years, 2% in 50 years was deemed a low risk, and we have the various categories of medium and high. The program right now is upgrading everything that was estimated as a high risk to upgrade those to a low risk. Similarly to the lateral deformation system, the diaphragms were all analyzed for inelastic behavior to get the maximum capacity out of this in an inelastic behavior. And again, probabilities of strain exceedance or displacement, either a probability and a conditional probability. And again, the various diaphragms are shown below here. Again, all those analyses that I mentioned. So what did this analysis entail? So those nonlinear backbone curves, the nonlinear degradation performance of all the prototypes I previously mentioned was analyzed both as lateral deformation systems, as diaphragms. And what was done was incremental nonlinear dynamic analysis from 10% to 250% of that code level earthquake to get these curves for each of the 3 types of earthquakes to move into the probabilistic combination, ultimately to get a probability of drift exceedance in the 50 years versus the factored resistance needed for that particular component. And so everything was a probabilistic approach to be consistent with the probabilistic approach of the National Building Code. So as I mentioned, the fundamental goal was a life safety performance objective, a probability of drift exceedance of 2%, probability that this drift right here over the 50-year lifespan of that building would not be exceeded for all the kind of earthquakes that we can see in British Columbia. In addition, there was a conditional probability check for just the 100% earthquake level. So 60 earthquake records run for just the 100% level, and a probability of drift exceedance of 25% as the strength degraded. So a little further performance, but still far away from collapse and collapse prevention. As I mentioned, for gymnasiums and auditoriums and cafeterias and the like, for shelter in place, an enhanced performance required that the components to behave at halfway between the yield drift and that design drift limit, so about in this range. So the seismic analyzer, and I'll talk more about it. So this was just, it's a tool to access all these pre-analyzed nonlinear dynamic analysis. And it's used to perform, as I said, risk assessment and obtain retrofit resistance for drifts that would provide that life safety performance level. And I'll speak more about this shortly. One key aspect about it, we call this a toolbox approach, is that the intent is to use all the capacity of the existing components in the school and only add the new as necessary. So, in this cartoon, we have to keep the vertical load systems carrying the vertical load for a given drift. The existing system can be damaged, but it contributes to the capacity, and we add the new components in a drift compatible assessment to make sure that life safety performance was met for the entire system. Out of plane heavy partition walls, we have kilometers of these in our BC schools. There were 4 prototypes assessed. The most typical one is this prototype we called OP3 for out of plane rocking. And as soon as the drift exceeded the thickness of the wall and we get collapse, we have that same probabilistic approach to make sure that those had that 2% and 50-year performance of not exceeding that drift. There was a lot of testing done at the University of British Columbia on the shake table. And again, these are masonry walls that we have miles of in BC. And we came up with we assessed many simple retrofits, this one being unistrut on one side of the wall. So the beauty of that testing is that we found very cost-effective solutions to implement on only one side of the wall to minimize disruption and interruption to the school program. And again, that one Chet showed was simple unistrut with masonry screws, not even connected to the floor above or below. Another really important part of the program was a special study we did on liquefaction. We have many schools in liquefiable areas. And what we found that the predictions using some of the previous empirical equations were too conservative for what we deemed inland schools. So schools more than 300 meters from the river or ocean and with a non-liquefiable crust of 3 meters or larger behaved very differently than those schools near the water's edge. So we used LIDAR to determine all the local terrain. We did analyses for a variety of schools and implemented simple guidelines that resulted in very significant savings for the mitigation of schools where liquefaction potential exists. So this was an excellent study that just completed about 6 months ago. So to the analyzer. So as I said, so this is this lookup tool for all those analyses. And again, it's very simple to use. You put in the community you're in, the site class of the school, one of those prototypes that I showed you. And for an assessment, the engineer has to determine the capacity, the resistance of that prototype, the story height, and the drift limit that's allowable to achieve life safety. You push the analysis button and it'll tell you, do you meet that probability of drift exceedance of 2% or not? This particular example shows, no, it should be 2%, it's 14, it's a high risk. Something needs to be done to upgrade this particular structural block in a school. So then again, for the same area, you select a prototype that is going to be now used for upgrading. Excuse me. And again, when you run the analysis, yeah, it tells you the lateral capacity as a percent W that's required to achieve that 2% in 50-year probability of drift exceedance for this drift to achieve life safety. So if you recall, in the previous slide, this particular building had 4% existing capacity. It needs 13.6. So the goal is now you only add a new structure with 9.6%. You combine the existing with the new in a cost-effective manner to achieve that performance that's expected. And again, so here's a typical school building. It had it's a prototype. It was deemed to be high risk. And what that analyzer allows you to do is to look at a variety of retrofit options. Perhaps you put a new shear wall here. Perhaps you put bracing. Perhaps you put it inside the school. Perhaps you do it, outside the school. And again, in this case, there's what is the drift required to protect these short columns to make sure their load can still be done, find out the demand that's needed, and then the engineers can find out what is needed as far as soil anchors, outriggers, to make sure the combined deflection of the foundation and walls is met. So the intent of the analyzer is to look at all these options. Sorry about that. So again, this analyzer is also used for autoplane walls. Again, to achieve, is that PDE 2% or 25%? And again, it allows the engineers to look at options of perhaps reducing the height and adding restraints to achieve the PDE and CPDE that's necessary. So these are just some shots of existing schemes that have been used, external wall upgrades, interior upgrades. Again, we used a lot of exterior wall upgrades to minimize disruption to the school, and some external piers. Our heritage buildings were upgraded conventionally on the inside. We used base isolation for some heritage buildings, and extensive use of FRP within stairwells, etc., in buildings that we found very cost effective. There's a lot of schools that required mitigation for liquefaction due to lateral spreading. And we developed what's called a ring beam concept, almost like putting a picture frame around the foundations of the school to prevent them from spreading laterally. And again, so structural horizontal beams were put around the building and in cases through the building in corridors or crawl spaces to ultimately keep those footings from spreading and potentially causing the vertical load carrying elements to fail. And at the end of the day, it just looked like a sidewalk to the passerby. Again, the other thing that we did is some full-scale testing to verify the retrofit capacity of these upgrades that were done. And here's a two-story school building, just the first story put on the shake table with the weight above it. And this was also done to do post-earthquake inspection training. We would bring structural engineers, have them look at the post-earthquake inspection and make a decision, would they allow students and teachers to go back into this building after the shaking. And this is that maximum credible earthquake for a particular site. So what's the status of the mitigation program today? 186 schools have been upgraded and each one might have up to 10 or 15 structural blocks. Like I said, not, a school consists of many, many structural components. So there might be approximately 2,000 buildings that have been upgraded. 29 are currently under construction, 13 in design, 19 with those project definition reports. And again, the rest are in the program to be addressed. $1.8 billion spent to date on the program. That's both seismic upgradings, and in cases where some of the very, very large secondary schools, it was deemed more cost effective to replace them completely with new schools. Engineers and Geoscientists of BC has endorsed these guidelines for every building in British Columbia to be upgraded using this performance-based approach for buildings up to 4 stories. And what's the future going forward? The next edition of the retrofit guidelines is in progress. It's due in 2023, and it's moving away from just that life safety or enhanced performance approach. A larger variety of earthquake intensities will be assessed. Higher performance levels, such as immediate occupancy, will be addressed. And resilience targets that for different levels of earthquakes will be implemented. And in addition to just being applicable for schools, the intent, of course, is to make this applicable for every existing building in British Columbia to use such a guideline. And again, the funding is available from the BC government to continue these retrofits. And my last slide here. So what is coming in a bigger picture rather than just the schools? In British Columbia, the Building and Safety Standards branch has a mandate to have an existing buildings code developed by 2024, and seismic resilience is intended to be a focus of that code. In Canada, there's a joint task group currently looking at a national code for existing buildings to be a target to be issued as early as 2025, including seismic performance requirements. So there's a large movement from the BC schools to every building in BC to every existing building in Canada to get something that is consistent so that all existing buildings can be upgraded to a variety of performance and resilience levels. So thank you for your attention. My apologies for running out of water partway through. And I hope that gives you a bit of insight to what is being done here in British Columbia. Thank you.